So this is an ongoing project with Mingi Kim and Sungun Lee. But some results have stabilized, so I'll talk about those, but there's also, I think, much more to be done. So let me tell you about the motivation, and I'm going to not say too many details, but just ask if there's something you want to understand. Something that's not clear, just let me know. Okay, so the motivation is something called Helly type theorems. Now, many of you maybe know this. It deals with convex sets in RD. Okay? So, for families of convex sets, and let's say finite families, let's even say compact convex sets, there is the famous Helly theorem. I'm not going to state it, I'm just going to write, there's a crucial number appearing there, d plus 1. If every d plus 1 members of a family of convex sets intersect, then they all intersect. Right? That's the basic Helly theorem. This is classic and important, not too difficult. There are more recent generalizations of this. There's something called colorful Helly. There's something called fractional Helly. And then there's even something called the PQ theorem. That's the name, PQ theorem. In all of these theorems, again, here there's the number d plus 1 appears, here the number d plus 1 appears, and here p is greater or equal to q is greater or equal to d plus 1. I'll say what these mean. No, I won't say exactly what they mean, but these are kind of combinatorial generalizations. And the main thing in all of these, they're sometimes called robust Helly theorems. Helly's theorem says every d plus 1 tuple intersects and you get some conclusion. Right? The robust ones are a weakening of this condition. Not every d plus 1 intersect, but some kind of system of d plus 1 of them intersect. This one says that instead of a single family of convex sets, you have d plus 1 families, f1 up to fd plus 1, families of convex sets. And whenever you choose a member from here, 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 those intersect. So only the transversals intersect. And the conclusion is that one of them is an intersecting family, has a point in common. Right? So you have no condition on any individual family. You only have these transversal conditions. Fractional Helly deals with just a single family, but all you know is that a positive fraction of the d plus 1 tuples intersect. So instead of all of them, maybe 50%, or maybe 10%. And the theorem says that no matter what percentage, as long as some fixed percentage intersects, then there's a point in common to a fixed percentage of all the members in the family. Right? And then the PQ theorem, this is one of the big achievements in this whole field by Alon and Kalai, says that if among any p there are some q that intersect, then there's a piercing number that's bounded. It means that there's a constant number of points, maybe 2,000, and every member intersects one of those 2,000 points. At least one, right? And of course, this constant piercing number should be independent of how big the family is or what it is. It only depends on dimension and on p and q. Right? So that's the famous piercing theorem called the PQ theorem. So this is very early. This is maybe 1913. These are from the early 80s. This is from the 90s. Yeah. Okay, and then what is the sort of ongoing theme in this field is we want to not deal with convex sets, we want more general sets. Okay, so more general sets, not assuming convexity. What can we say? And our work was motivated by a question by Xavier. So, question by Xavier Guoc, who, together with some co-authors, recently made a very general Helly-type theorem for a very general type of sets. I'm not going to go very much into what their theorem says, but they can only do a Helly theorem, and it partially comes from the method they use. And the main question is, what about these guys? Can you generalize this to more general sets? Right? How much of this theory goes through for these general sets? And the first case that they cannot do at all by their methods is the following. So F is going to be a family of open connected sets in the plane. So that's the simplest case that they're trying to deal with, right? Now, in general, there's no Helly theorem for these. You cannot have that. It's too loose of a definition. But we need to copy something more that comes from the convex sets, and that is that F is, some people call it intersectional. And what that means is that every intersection is, well, empty or connected. Right? So you need this hereditary property. You have it for free here, because the intersection of convex sets is convex. Right? And you need some kind of intersectional property to have anything of this work. And so that's the assumption they do here. And so such a family, intersectional family of open connected sets, well, it has a Helly theorem, and let me show you that. That's a very nice. So Helly theorem, what they call the Helly number for these families is 4. If every 4 intersect, then they all intersect. Right? Now let me prove this for you. Okay, so proof, and let me just do the case when the family consists of 5 sets. Okay, so you have 5 sets, they're connected, and whenever they intersect, they're connected. I use open because that guarantees that they're path connected. That's somehow important for me here. Okay, so I have 5 sets, so let me label them 1, 2, 3, 4, 5. And here's a point. Say that's in the intersection of 1, 2, 3, and 4. Right? And here's a point in the intersection of 1, 3, 4, and 5. Okay? It means that there is a path inside the intersection of, let's see, 1, 3, and 4. 1, 3, and 4 contains this point. 1, 3, and 4 contains this point. Since it's intersectional, there's a path that connects them. Right? Maybe here's a point contained in 2, 3, 4, 5. Here's a point in 1, 2, 4, 5. Now look what happens if these intersect. So this, let me draw a different color here. This path is contained inside 2, 4, 5. This path is contained inside 1, 3, 4. This intersection point is contained inside all 5. Right? It's contained inside 1, it's contained inside 2, inside 3, inside 4, inside 5. So this guy is in all of them. So all I need to guarantee is that there's such an intersection point between these paths. But that will happen. Do you see why? Yeah, there are 5 members in my family. For any 4, you can draw a point. Right? So you have 5 points. Any 2 points can be connected by a path which contains 3. So you drew K5. And there must be an intersecting pair of edges, so that proves the theorem. Yeah? And then you can do for 6. Now you know that every 5 intersect. So then you do over again. Pick a point inside every 5 tuple. You pick 6 of them, you pick inside every 5 tuple. Same way you draw K6. It's still not planar. There's an intersection, and you get it. Yeah? And so on. And this was the idea that this is I don't know where this proof comes from. Somehow everybody seems to have known it. And what Xavier and them did based on work by Matuszek was to generalize this to more general sets. And you can easily go to higher dimensions. There's something analogous to this non-embeddability of K5 called von Kampen-Flores theorem. And then you can do higher dimensions. You cannot deal with connected sets anymore. You need simply connected in R3 and R4 and so on. Right? But it's sort of very straightforward. What they did and what Matuszek did is not straightforward. They allow for even more complicated sets. Okay. So all of these, everything that they did here, this is based on what we can call non-embeddability. That's where it comes from. And as nobody has been able to get these kind of theorems from that non-embeddability. Right? That seems to be the problem. So that was our starting point, and so Xavier asked, well, how can we get this? Right? How can we get these kind of theorems for this general setting here? Okay, so now let me switch a little bit. Yeah, so this is basically about piercing numbers. Yeah? Now let me go to nerves. So suppose you have a family of sets, S1, Sn, and I can associate with this a simplicial complex called the nerve of F, and this is the family of subsets of the index set. So these are non-empty sets. Such that the intersection of Si. Okay, so this is an abstract simplicial complex. Okay? Any subfamily that intersects becomes a face in your simplicial complex. And this is very useful when studying these kind of piercing theorems, because essentially these piercing theorems deal with the intersection patterns of these sets. All right? And so if this was a family of convex sets, we can look at the nerve complex. And what does it mean that they all intersect? Well, it means that the full simplex on n vertices is the nerve. Right? What does it mean that there are 2 points that intersect all the members? Well, it means that there are 2 faces in the simplicial complex that cover all the vertices. Right? So everything about piercing numbers can be encoded by the nerve. The nerve encodes the intersection patterns of the sets. Right? So far, this really doesn't say anything. But what is very useful in this field and in other areas is something called the nerve theorem. And informally, a nerve theorem, this relates the topology of this abstract simplicial complex to the topology of the union of the sets Si. That's what a nerve theorem, what you want a nerve theorem to do. Right? But in general, there is no relation between, well, this is just a family of sets. There isn't even a topology here, right? But when we use this, let me change my notation here a little bit. Ki, F, K1, Kn. These are simplicial complexes. Then a nerve theorem relates the topology of this abstract complex to the union of these simplicial complexes. Right? And still you need a condition. So this is provided the intersection of anything So what does it say? It says that whenever something intersects, right, that intersection must be nice in some sense. And if the intersection is always nice, then you really get a relation between the topology here and the topology here. Right? what does nice mean? Nice means, for example, contractible, or K-connected, or acyclic, or K-acyclic. These are just various homological terms for saying that something is nice. Topological terms, sorry. This is homotopy. This is homology. And so somehow, as long as those intersections are nice, there is a relationship between these two. Okay? Now, how does it relate to, for example, these Helly theorems here? So, in particular, contractible. The case when the intersections are contractible, this is a version of the nerve theorem called Boursock's nerve theorem. Okay, so if the intersection of any of the sets is contractible, then Boursock's nerve theorem says that this and this are homotopy equivalent. So that's as strong as you can get, essentially. Right? And that's what's used to study convex sets in RD. Because convex sets are contractible, so therefore, automatically, the nerve of a family of convex sets must satisfy Boursock's nerve theorem. Right? But then, here's an observation. Or I should rather say note, but let's say compact subsets in RD have zero homology. In dimension greater or equal to D. This is just a fact. You'll have to accept it. Right? For example, simplest way to make D-dimensional homology is by making a D sphere. But you cannot take RD and fold it around and make a D-dimensional sphere. You're changing the space. Right? And this is it turns out, so Kalai, Meshulam, Kalai and Meshulam and others, they showed that actually many of these theorems over here follow just from this. So what they do is, you take a family of convex sets, you look at the nerve complex. Now, you satisfy Boursock's nerve theorem, so the nerve complex is homotopy equivalent to the union of those convex sets. The convex sets live in RD, they're compact, so their union is compact. And it's a compact subset of RD. So there's no homology in dimension greater or equal to D. And that transfers back to the nerve and says there's no homology in dimension greater or equal to D in this nerve complex. And the same for any induced subcomplex. Because induced subcomplexes of the nerve, well, that's just deleting some of the sets. And so what they showed is that actually all of these things follow from just this combinatorial condition on the simplicial complex. Okay, so I call it a combinatorial condition because it really is just a combinatorial condition. Right? So what you use the nerve theorem for is to say that those complexes, intersection patterns that come from convex sets in RD, cannot be too complicated. So this is a bound on the complexity of the nerve. Some kind of bound. Right? That's what this is used for. And so that's how we want to approach Savier's problem, by saying that, well, the complexity of these kind of nerves that arise from these sets cannot be too complicated. Should immediately give us these kind of things. Yeah? Okay. So that was a quick introduction to how we relate the nerve theorem to these piercing numbers. Okay, so now I'm going to switch gears again, and I'm going to consider graphs. So why do I consider graphs? Well, I'm dealing with connected sets. And it turns out, when you think about it, so we thought about it, and it turns out that graphs are really enough to capture connectivity, or connectedness. Right? So what we want to do is the following. Consider a family F, G1, Gn. These are connected graphs. Okay, so what can the nerve of this family tell us about the union? So you should think of these as a family of graphs living inside a graph, and their union is the total graph, right? So essentially it's just like the nerve theorem, right? Except, well, what is it I need in the nerve theorem? I need that intersections should be nice, and I want to get something out. I want to get something out about the union of these graphs, right? And I can, for example, consider graphs as one-dimensional simplicial complexes, and I can just apply Boursuc's nerve theorem, for example. That won't get me very far, because I need these to be nice, for example, contractible. The only contractible graphs are trees, right? And what I will get out so if this is a family of trees covering some graph, what do I get out? I get out something about the topology of that graph. But the topology of a graph is usually very uninteresting. It'll tell me the fundamental group of the graph, and the fundamental of the group of the graph essentially contains no structural information about the graph, right? So it's not too good for me. Do you agree? Or the homology will tell me about the cycle space, but only about the dimension of this thing. So it's really little information you get. Yeah. Okay, so that's why I'm going to weaken my assumption a little bit. I'm going to take as input just arbitrary connected graphs. They don't need to be contractible. And nice intersection, well, it should be intersectional. This just means connected. So now I have a family of connected graphs, and their intersections are connected. That's it, right? What can then this tell me about this? Well, not very much. You can take as complicated a graph as you want. You can cover it by one graph itself. The nerve is a single vertex, and it does not reveal very much about the structure of the graph. So we need to modify it a little bit, or what we need to consider is something more subtle. So I'll call this a connected family. Connected family in a graph G. Okay? And I'm not going to require that they cover the entire graph, just a family of induced subgraphs that are connected. This will be a connected family in the graph. Okay? Let me write here specifically the intersection I and sigma gi is connected for every sigma in the nerve.
You allow it to be empty?
Yes. You mean here?
I mean the intersection.
Yes, of course, because you only require it's connected for sigmas in the nerve. If it's empty, if the intersection is empty, it's not a face in the nerve. Yeah.
So still it's intersectional then.
Yeah. Okay. And so what it turns out is the thing to study, at least what we found. Right, did you have something to say? No. Is some graph parameter which we call the homological dimension of a graph. So G is some fixed graph. I'll define gamma G is the maximum D such that and I'm going to take the maximum over F is a connected family in G. Okay? So you have this graph, you look at all possible ways of putting connected families inside there, you measure their homology of the nerve complex, and the highest dimension in which you can get homology, this is the homological dimension of the graph. Okay? And so this is the parameter that we ended up studying and turned out to be crucial. And so as the project went on, actually we kind of lost interest in this. These are just basic consequences. This parameter became more and more interesting. Right? Now, let me see. By definition, I'll set the dimension of a single vertex -1. That's just to make things look okay. Now here are some basic facts. Oh wait. All right, so I want a nerve theorem. I want to study it through here. What does the nerve tell me about the union? Yeah, so what is the structural information I want? I told you the topology or the fundamental group of the graph is not interesting to me. But what I am interested in is something more structural. And so here, graph minors becomes a crucial concept. That really captures structure. And this is related to graph minors because here's a property, properties. It's minor monotone. If H is a minor of G, then the dimension of H is less than or equal to the dimension of G. Right? This is sort of a very basic property about that parameter. Another basic property, of course, on the complete graphs, Kn, this is n minus 2. That's the dimension of the complete graph. And it shouldn't be too hard to see. Let's start with K3, for example. K3, well, it really looks like, topologically, this is a circle, right? It's a one-dimensional homology. Yeah, you get that. What about this? Well, it kind of looks like a tetrahedron, right? That's the surface of a two-dimensional, that's a two-dimensional sphere, right? And you get two-dimensional homology, not more. And so on. K5 is like a 4 simplex, K5 is like a 6 simplex, and the boundary of this, right? It all matches with that very nicely. Okay. Yeah, so I can just write here that this is kind of looks like n minus 2 sphere.
So in that case, connected family would be the collection of all connected induced subgraphs?
No. The collection of induced subgraphs you get by deleting a single vertex. Oh. So for every single vertex you delete, well, probably one you said will work too, but it will be a much thicker sphere. It will be homotopy equivalent, I guess. Yeah. But it's enough to just consider the family of subgraphs with one vertex less. It will give you exactly a nerve which is the boundary of the n minus 1 dimensional simplex. Okay. Okay, so this of course means that if Kn is a minor in your graph, then your homological dimension is at least n minus 2. Let me continue over here. No, let me just continue there. Never mind. So here is one of our results. All right, so when we, after defining this, took some time to come up with this. This observation became very interesting, and the question is, does the converse hold? Right? If the homological dimension is large, does it mean you have a large complete minor? Right? And so for any graph G, and although I'm not saying it, writing it, usually we just consider connected graphs. It's not really a big restriction. So K3 is a minor in G if and only if the dimension is at least 1. 2, K4 is a minor in G if and only if the dimension is at least 2. 3, K5 is a minor in G if and only if the dimension is at least 3. And that's how far we could get. But the reason we are okay to stop at this point, well, currently is that this case implies the Helly theorems that Xavier asked. Right? So that's why we're okay to stop there. Now, why is that? He considers, here's one of the sets, yeah? Open connected set. And you have a bunch of them intersecting here. Well, what you can do is you just approximate this by some graph. You just triangulate this very, very finely, the whole plane, and you just approximate the sets by graphs. Do it fine enough, then the intersections will also be encoded by subgraphs that are connected. So every connected family of open sets is a connected family of graphs in a planar graph. Right? Planar graph has no K5, so there's no K5, so the homological dimension of that family, the homology cannot must be 0 in dimension 3 and above. Right? And then, like I said, Kalai and Meshulam already figured out that with that bound on the complexity of the nerve, you start getting these Helly theorems. And in particular, we get all the ones that he asked for. Well, you get colorful Helly with Helly number 4. You get fractional Helly with 4 and PQ greater or equal to 4. But then it turns out that if you do a little more combinatorial work, you can get this down to 3 and this down to 3. This one you cannot get down. The Helly number really is 4, so you cannot go below that. But for these other ones, you can even reduce it even further. So it really looks like it does for convex sets. All those holes in your sets, they don't really matter. Strangely enough. Yeah. Okay. So let me mention a few more things. Now here's a crucial lemma. So if G is a clique sum, G1 and G2, gamma G equals the maximum gamma G1, gamma G2. So there's another nice property of this invariant. If you know, do you know what a clique sum is? Yeah. Right, so you have a graph G1, you have another graph G2, and since I want things to be connected, I'll not consider the 0 clique sum. Here's a clique in this graph, and you have a clique of the same size in this graph, and then you just identify the vertices here. Right? Glue them together. So it's just gluing graphs together along cliques. And you can show this by, it's not too hard, you apply Meyer-Vietoris. And a little bit of argument, and then you see that this holds. Okay? So you don't increase the dimension by doing clique sums. And so then it's easy to prove the first two cases. Right? So if you want to prove 1, well, suppose you have G, suppose K3 is not a minor in G. Let's assume G is connected. Then G is a tree, right? And it turns out, well, G will then be a subgraph of K2 plus K2 yeah? Yes, you get a tree by just gluing edges together. Yeah. And so therefore, you get this one. Because the dimension of K2 is 0. Yeah? And then 2, suppose K4 is not a minor in G, then G is a subgraph of K3 plus K3. This means clique sum, by the way. Right? I think this is also a well-known theorem. And gamma K3 is 1. Right? So you don't increase there, and so that proves part 2. And then things change a bit when we get to K5. Those of you who study graph theory, but the graph theoreticians here know this very well, of course. What about 3? So suppose K5 is not a minor in G. Then G is a subgraph of clique sums, G1, G2, Gn, let's say, where Gi is a planar graph or a specific graph called W8, the Wagner graph, which looks like you take an 8 cycle and then you join antipodal vertices on that cycle, right? Now, if you take cliques of planar graphs and the clique sums of planar graphs and these, then you will contain any graph that has no K5 minor. Okay? And then you compute in one way or another that the homological dimension of W8 is 2, and then you compute that for any planar graph G. But actually that is not trivial. So I'll even call this a theorem. I would say this is our main theorem, because that is not trivial. And of course this is all you need to prove Savier's question. It's really the planar graphs he's asking about, right? And that is the non-trivial case. But the interesting part is that actually this seems to be related to complete minors, this homological dimension. And we would like ideas on how to proceed further, K6 minors and so on. Okay, so maybe I have a few more minutes, so let me explain a little bit about this crucial part here. And for this, the key thing we need is a combinatorial identity. And this identity to me is very mysterious, and I've contacted topologists and they do not know either what this is exactly. I hope Dongsu, maybe you can tell me. Okay, so I'll explain it in homological terms and I'll also make a translation to what it means combinatorially. It's just combinatorics. So tau is a sum, and this is a simplicial 2 cycle. And I'm going to say what this means afterwards. Maybe I'll say it now. All this means is that tau is, by the way, Z2 coefficients. My homology is with Z2 coefficients. That's what makes it combinatorial. So tau is a set T1, tau m, tau I are three subsets of some finite set. Every two subset appears in an even number of tau I. That's all this statement here means. Okay, so you have, say, a hypergraph on three uniform hypergraph. Every two element subset appears in an even number of those. Okay, an even number of these guys. This is translated, this is a simplicial two-cycle mod Z2. Okay? And now I'm going to construct a simplicial 3-chain as follows. First of all, you order these sets here, these triples. So order, say tau 1 less than tau 2 less than tau m. Okay? In fact, all you need is a cyclic order. You place these on a cycle. Here's tau 1, tau 2, tau 3, etc. And then consider whenever you have tau I less than tau j less than tau k less than tau l. So for any four which are ordered like this, okay, where tau I intersect tau k, they share a two-element subset. Tau j intersect tau l share a two-element subset, and tau I intersect tau k union tau j intersect tau l. So these two subsets, this size is 4. Okay? Then this set here, this set is in my simplicial 3-chain T. Okay, let me explain what this is. So tau I less than tau j. Okay, so here's I, here's j, here's k, here's l. Okay, all it means is that when you draw this segment and you draw this segment, they cross. Right? That's what this ordering means. Okay. And then you need tau I, tau k. These are two triples. They should have a two-element subset in common. And these two should have a two-element subset in common. And those two-element subsets should be disjoint. Their union should be a four-element subset. And that gives me a four-element subset, which is a 3-simplex, which goes into my 3-chain T. Okay? So now you get a collection of, you do this over all possible of these, all possible quadruples that intersect, that are ordered this way and like this, satisfying this. You just get a collection of 4-element subsets. You mod out by 2, so you take only ones that appear an odd number of times. That is T. And this is a 3-chain. Okay, so this is a set of 4 subsets. Okay? So this is a construction. And the identity, what I call the combinatorial identity, is that the lemma, the boundary of T, this depends on the input cycle and the ordering that you gave. Boundary of T tau order equals tau. Okay? Yeah, it looks like nonsense, but what this means is, okay, you start with a bunch of triples. Every pair appears an even number of times. It could be 0, right? Now you order those triples whatever way you want. You make this strange construction when they are non-separated like this, right? And they supported by distinct pairs. Then you take the union of those two pairs, you get a 4-element subset. You put it into this guy. Now you take the boundary of this 4 chain. Now what is the boundary? It's a set of triples that appear an odd number of times in those 4 tuples. And you're going to get back exactly this one. And that's the identity. Okay? And this guy really depends on this ordering. If you change the order, this thing will change. It will be a different family. But what's invariant of that family is that the boundary is always the guy you started with. Right?
So what do you mean by boundary? It's a collection of 3 subsets?
Yeah. So boundary, so in this case, boundary of T equals the collection of 3 subsets appearing in odd number of 4 subsets in T. Right? And so, I mean, here, the boundary of this guy here would be the number of pairs appearing in an odd number of those tau, right? And there is no boundary. That's what makes it a cycle. Okay. And so this we can prove. Proof is kind of nice, but we don't really know what it means. And we would like to know what it means. Yeah. Okay, so now let's go back to this guy. So I have a few minutes, so I'll show you how this all fits together now. So I want to prove that G planar, then gamma G is at most 2. It'll just be a sketch. Okay, so suppose you have this family, G1 to Gn. This is connected family. Let's say the union of the Gi equals G. And suppose it's a minimal counterexample. Minimal counterexample. And then you can show that this means we assume that the 3-dimensional homology of the nerve of F is non-zero. Okay? Right, so I want to show that there is no homology in dimension greater or equal to 3. So this is my counterexample. There should exist such a thing. You prove that. And you also prove that may assume G is 2 connected. G and every member in F are 2 connected. Now I mean 2 connected in the graph theoretic sense. And what this means is that you fix an embedding, every face is bounded by a cycle. Right? That's what I need. And so the basic idea of the proof is very simple. I have here F. This was G1 to Gn. That's my counterexample. It has a nerve. Let's call it K, a nerve of F. And what I'm going to do now is I'm going to fix one guy. I'm going to fix this guy, Gn, and I'm going to change Gn a little bit. So one of the members, I'm going to change it, get F prime, G1 up to Gn prime. And I get, of course, a new nerve over here. K prime is the nerve of F prime. And my goal, my hope is that when I change that thing, the nerve will change, but the 3-dimensional homology survives. Okay? And the way that I'm going to change the graph is, so let's look at Gn. It's here, and here's a face. Here's a face of Gn. And there are a bunch of vertices of G inside here. Okay? So these are vertices of G that are not in the graph Gn. And they're inside this face. And what I'm going to do is, I'm going to add these vertices to the graph Gn. So I'm fixing a face. I'm going to add the vertices to Gn. Right? So Gn is going to grow a little bit by getting some new vertices. I'm always taking induced subgraphs, so you, of course, include the new edges that appear here. Right? So this graph got a little bigger. It's maybe going to intersect a few more things, so the nerve is going to become a little bit bigger. Essentially, you can think of, there's a natural inclusion here, so you can think of that the nerve is growing, becoming a slightly bigger complex. And my goal is to say that while the three-dimensional homology here was non-zero, then it must also be non-zero here. And that's a good step, because then I can continue. I can go to another face of Gn and fill in those vertices. Right? And if I know that the three-dimensional homology doesn't vanish, then that's good. Then I do it again and again and again and again. And how long can I do that? Well, I can do that until there are no more vertices to put in. But then Gn equals the graph G. Right? Then Gn is the graph G. And if Gn is the graph G, then the nerve is just a cone, and it's contractible. It has no homology. Which means that it must have started here with 0 homology in dimension 3. Okay? Okay, so I do this, I fill it in, and I need to understand how does this change. Well, you have the vertex in the nerve, Vn, corresponding to the guy Gn, who's changing. Right? And there are a bunch of things that he didn't intersect, but when you fill in those vertices, he starts intersecting new things. Right? And those are the new simplices you're adding. Simplices that extend down to Vn. Okay, so let me write formally here. So suppose gamma, gamma is, I'm misusing the notation here a little bit. I take a non-zero element in the homology here. I look at that cycle, right? And suppose that gamma equals 0 in H3K prime, right? So suppose this doesn't work. Suppose that when I fill in those simplices, filling in those vertices there, that guy that was non-zero now becomes 0, right? Just imagine you had this, if I'm in dimension 2, there was a sphere, it was nice, I couldn't close it, but when I added in this thing, suddenly this thing closed and that hole disappeared, right? That's what's happening here. And then you can show that gamma equals beta plus something like this. What this means is beta is a 3-chain in K. Okay, so I'll try to draw a picture of what this looks like. So it means that you have here beta. This is an intersection. This is a bunch of 4 tuples that intersect, right? 4 tuples in F that intersect, right? Boundary beta is really the boundary here. And here is Vn. And so you're taking beta and you're adding the boundary coned with V, which means this boundary here, right? So that is precisely such a non-zero element of the homology, right? It's empty inside here. Just imagine this, if again in two-dimensional homology, you have a disk, you have a point below and you cone up to the boundary of the disk, that's going to make this hole, right? And what's happening, if this guy dies, you're filling in that hole. And you can prove that this is what it looks like. Okay. Let's see, boundary of beta. That's a set of triples, right? This is a 3-chain. It's a set of family of 4 tuples. Then you look at the set of triples that appear in an odd number of them. They intersect V. So they intersect on the inside here. They also intersect Vn. They intersect out here, which means those triples have representatives. Every triple in this boundary lies along this cycle here as well. There's an intersection of those triples that lie along this cycle here. Okay? And I can call those tau 1, tau 2, tau 3. This is the sum of tau I. This is the boundary of beta. And that's where this thing is going to come into play, right? I erased the crucial picture. I'm sorry. And they also come ordered along this cycle, right? Which means I have that ordering that I want. And now I want to claim that this guy, T tau order, is really in my nerve. Those 4 tuples that intersected here, they live inside the nerve. And how do I see that? Well, let's look at tau 1, tau 3, tau 2, tau 8. So suppose tau 1 and tau 2, that's a triple that intersect here. There's another triple that intersect here, and they have a pair in common, right? But this is a connected family. So that pair intersects Vn here and intersects Vn here. And since it's a connected family, there must be a path that connects them. So it connects like this within the graph Vn or Gn. And tau 2 and tau 8, they have a different pair in common, right? They intersect, and they must go from here to here, and they must cross. Yeah? So I get that simplex in the nerve. So it means that this guy, tau T order, is something in the nerve. Yeah? So T tau sigma is in K minus Vn, actually. Okay? And then, what is the boundary of this guy? So T. But the boundary of this guy, boundary T, well, it's the same as that original cycle, this guy. Okay? Which means that beta plus T is in K minus Vn, and beta plus T boundary equals 0. That is a cycle. And since I assumed that everything was minimal here, it's a cycle that lives inside the nerve where I deleted this guy. This is contractible. You can fill in this hole. And then you can use that hole to fill in the original hole, showing that actually gamma was 0 from the beginning. Okay, so I'll skip the details here. So essentially what you're doing is you're using this guy to show that, well, outside here, there lives something else that closes that hole already. Meaning the whole gamma did not die when I went from here to here, because it was already 0 when I started here. It was already dead. Yeah? And that completes the proof. But everything hinges a lot on that combinatorial lemma, which I think we need to understand what it means to be able to extend further. Yeah. Okay, so I think I'll finish there.